Hello everyone, my name is Cao Thang Ding. I am an assistant professor of chemical engineering at Queen's University. Thank you for inviting me. And today I would like to talk about gas diffusion electrode for carbon dioxide conversion to fuels and chemicals. With this topic, I will first introduce about this technology, why do we want to do that, and some fundamental aspect about this system. And I will then focus mainly on how we're going to design a efficient gas diffusion electrode for this process. Currently, we emit about 40 gigaton of CO2 per year, and more than half of it stay in the atmosphere. And that's why the CO2 concentration has increased rapidly over the past few decades. And that leads to the global warming. If we continue to emit the CO2 like what we are doing now, we are on the path of increasing our global temperature of about 3.6 Celsius degree by the end of this century. And if we want to keep the global temperature increase below 1.5 Celsius degree, which is the blue scenario here, like what our target. So we need to somehow bring down the CO2 emission from 40 gigaton per year to zero at some point in the near future, about 50, 60 years from now. So just give you a sense of 40 gigaton of CO2, that is 100 times larger than the total body weight of entire human population. And that's a huge amount of CO2. So where does this come from? So CO2 comes from different sources, but the energy sector is by far the largest CO2 emitter. It accounts for more than 70% of total CO2 emission. And it is not a surprise because more than 80% of our energies come from the fossil fuels like gas, oil, and coal. And when we burn them, we emit CO2. And less than 20% comes from the renewable energy. So if we want to tackle the CO2 emission, we need to think about the different source of energy. And the good news is we have a lot of renewable energy like wind and solar. For example, the amount of energy solar shine on Earth is 9,000 times the amount of the global energy demand. So if we can just capture a small fraction of solar energy, that should be enough for us. And in comparison, the energy that we are relying now based on the fossil fuels, they are the finite resources. And if we continue to use those energy like what we are using now, they are going to running out in about 100 years. So whether or not we care about the CO2 emission, just from the energy point of view, we still need to think about the renewable energy at the future sources. The renewable energy is great, but there's a big challenge facing this type of energy. And it is the intermittency. The renewable energy like wind and solar, and they're not always available. The sun doesn't shine all the time. The wind doesn't blow all the time. For example, the solar irradiation vary every hour, and we have only a few hours of irradiation every day. And depending on where you are located in the globe, you may have the significant change in solar irradiation at the different seasons. So if we want to rely on renewable energy, we need to find a way to store them so that we can use them later, not just for hours, for weeks, but for months and possibly for years. So the technology that we are working on is called electrochemical CO2 conversion. So the idea is to take the CO2 emitted from power plant or from transportation. We capture those CO2 and we use the renewable electricity as the energy sources to break down the CO2 molecule and convert it into the chemicals like similar to the molecule that we get from the fossil fuel. So by doing that, we can store the renewable electricity in the form of liquid or gas fuels that we are having now, and they can be easily integrated to the current infrastructure. So how we are going to do that? So this is a electrochemical process, and in principle, you will need a anode and a cathode. And on the anode side, the water is oxidized to produce oxygen, proton, and electron. And the proton and electron move to the cathode side, where they will reduce the CO2 into the different molecule. And in general, you have a membrane between the two electrodes so that you can separate the reactant and products, but you can keep the charge of the system balanced. And also depend on the type of the catalyst, you can make different products here. Especially if you use the copper-based catalyst, you can make different type of hydrocarbons in the gas phase or in the liquid phase like methanol and ethanol. So from the system point of view, how are we going to carry out this reaction? And in principle, you can do that in two different ways, depending on how you fit the CO2 into the system. So the first system is called Aqueous phase system, where the CO2 is dissolved in an electrolyte before it can fit to the surface of the catalyst here. And in this case, the catalyst is deposited on a solid substrate. So in this system, as you can see the zoom in here, so the CO2 dissolved in the electrolyte will diffuse to the surface of the catalyst where it is reduced to the products. And in that system, like the CO2 needs to diffuse a pretty long path here, normally around 50 micron. And because of this long diffusion path here, we have a limited amount of CO2 on the surface to be converted. So that's why we have a limiting current density, usually of around 50 milliamp per square centimeter. And in order to have this technology to be commercially competitive, you will need to run the reaction at a current density of few hundred milliamp current density so that you can reduce the capital costs for the system. Now, one way to do that is to use a gas phase system. So the difference here is that the catalyst is now deposited on a porous substrate instead of a solid substrate like the previous system. And here, the CO2 and the electrolyte are provided to the surface of the catalyst in the two different paths. So the CO2 coming from the back and the electrolyte coming from the front of the catalyst layer. So as you can see here, this is the zoom in of the system where the CO2 diffuse through a porous layer to the catalyst surface. And the electrolyte is coming from the front of the catalyst here. And the porous layer here is called the gas diffusion layer. And normally it is the hydrophobic layer and it's also conductive. And the key thing in this technology is how you can make the the efficient gas diffusion electrode for this system. And that's the main target of my research over the past few years that I would like to share with you today. Okay, so let's take a look at the gas diffusion electrode here again. So the key thing in designing the electrode for CO2 conversion is that we need to manage how we bring the electron, we need to bring the water and CO2 to the one active site at the same time, because those are required reactants to produce different products. And that is challenging because each of them need different ways of transportation. So that's why it's not straightforward to design the system for that can satisfy all of these demand. The traditional way to achieve this goal is to have a carbon-based gas diffusion layer and then a catalyst layer on top of it. So in this structure, so the CO2 and electron going through this same way here. So electron go through the carbon network, while the CO2 diffuse through the porous structure. So it's because of the porous carbon here. And it's because it is hydrophobic, so that the water cannot penetrate in here. It can only reach the surface of the catalyst without penetrate deep into the gas diffusion layer here. So that is the typical way of making the gas diffusion electrode for CO2 reduction. And when we start working on this technology, we use commercial gas diffusion layer here, which is the carbon gas diffusion layer. This look like this. It has two layers, like the black one is a microporous layer made of carbon nanoparticle, and that's the front layer, and is the backing layer is the carbon fiber, which good conductivity and is also hydrophobic. So we use the carbon-based gas diffusion layer, and we deposit a layer of the copper catalyst on that using the physical deposition method. So first we start with a catalyst layer of 100 nanometer thickness. And we try different electrolytes. So the previous study has showed that the alkaline media is good for CO2 reduction to multiple carbon products because it favors the coupling process to form those products. So first we try to use electrolytes, basic electrolyte with the different concentration, increase the pH of the solution from 1 molar potassium hydroxide to 10 molar potassium hydroxide. And we found that when we increase the potassium concentration, not only we reduce the overpotential to form the ethylene here. So here the ethylene for efficiency versus the applied potential versus the reversible hydrogen electrode. So on if it's go to the left-hand side, you will have the smaller overpotential. And here on the right-hand side, you have larger overpotential. And it's interesting that we observe not just the decrease in overpotential, but also we observe higher selectivity for ethylene when we go to the higher K-risk concentration. So after optimize the electrolyte, we further optimize the catalyst layer by changing the thickness of the catalyst layer. So we deposit the catalyst from 10 nanometer, 25, and then 1,000 nanometer. And then we operate the system, CO2 reduction in the high K-risk concentration. So what we observed was the thinner catalyst layer seemed to perform much better compared to the thicker one. So here again, the ethylene Faraday efficiency versus the current density. We observe like optimum current density for different catalysts with a different thickness from 10 nanometer to 1000 nanometer. We also have a control sample of copper nanoparticle, and then we deposit with the similar thickness. So by optimizing the catalyst, we observe that the red one here is the copper with 25 nanometer thickness, exhibit the highest selectivity of around 60–65%. And we observe this high selectivity at very low overpotential of only 0.55 volt, which is the lowest one that we observe like based for the CO2 reduction to ethylene. And we observe it at pretty good current density of 275 milliamp per square centimeter. And taking together from the Faraday efficiency and the low overpotential, we have the half cell energy efficiency of 45%, which is 1.4 times higher than the best previously reported. So everything seemed work very well, except the one thing, when we try to run the stability of the catalyst, what we observed was the ethylene selectivity decreased rapidly, like within an hour or so. It's like half an hour is decreased from 60% to around 30%. And at the same time, the hydrogen and methane seem to increase. We try to understand why and what happened to the catalyst layer or the gas diffusion layer. And by characterize the catalyst and the gas diffusion layer after the reaction, we found that the surface of the gas diffusion layer changed from the hydrophobicity to the hydrophilicity. As you see, the change in the water contact angle here. And as mentioned previously, once the gas diffusion layer changed to the hydrophilicity, the water from the electrolyte will penetrate through the gas diffusion layer. And in that case, it blocks the CO2 to diffuse to the catalyst layer. Now, instead of having a gas phase CO2 reduction, you won't have an accurate system, because now CO2 needs to diffuse through a very long path to the catalyst surface, especially if you run in the basic media. It's not possible because the CO2 will be converted to the carbonate before it can reach the surface of the catalyst. So what we did was we reconfigure the gas diffusion electrode. So instead of using the carbon-based gas diffusion electrode, we use a polymer-based gas diffusion electrode. And what we found was we use the PTFE, a very stable polymer under the basic condition. And we use the PTFE membrane to deposit the thin layer of the catalyst on that. Now the PTFE layer is porous. It can transfer the CO2 through that layer, but it cannot transfer the electron like the carbon-based gas diffusion electrode. So electron need to go through either catalyst layer or another layer. So in order to improve the electron transport, we add a layer of the carbon nanoparticle and the graphite on top of the catalyst layer. So now the CO2 and the electron goes in the different direction to the surface of the catalyst, right? Which is different from the carbon base. So we decouple the path for CO2 and electron. The way we make this sample is we start from the porous PTFE membrane, and then we use the sputtering method to deposit a thin layer of the copper. So we call it the copper on PTFE. After that, we spray a thin layer of the carbon nanoparticle and another graphite layer on top. So here the scanning electron microscopy images of the sample at different stage, just confirming that we have successfully deposited each layer on the porous PTFE. And the sample worked very well in terms of stability. As you can see here, the copper on PTFE sample can maintain a good selectivity of around 65 to 70% of ethylene for more than 150 hours. While like the carbon sample, again, it's just like did not functioning after an hour or so. We have also another control sample of the graphite on copper on PTFE without using the carbon layer. It also worked, but with lower selectivity for ethylene, and also a little bit lower in terms of stability. By deposit the copper graphite on the PTFE, we maintain the reaction for 150 hours, which is like an order of magnitude longer than the previously report for CO2 reduction to ethylene. We also confirm the structure of the catalyst after the reaction, that we can still observe the distribution of the copper and nanoparticle and carbon and graphite throughout the cross-section SEM here. Okay, so the PTFE worked very well for the stability, but there's one problem though. So as you can see here, even though we have the gas diffusion layer, we have PTFE there, the optimum current density is pretty low. Normally, we operate the system within like 70 to 100 milliamp current density, which is not much higher than in aqueous system. And remember, we may need like the current density from 300 to 500 milliamp current density to be economically viable for this system. Now we just take a look again at how the CO2 diffused to the active side, and then we will see that if we can further improve the current density for the copper on PTFE. So remember that we need to transport this not just CO2, but also electron and water to the active side. And here again is the copper on PTFE substrate. If you look carefully to this structure, so the CO2 can diffuse from the back of the PTFE, and then once it reaches to the surface of the copper, here the electrolyte is occupy the surface of the copper. So the active CO area is very small because of like you have the gas, you have the liquid, and you have the catalyst here. So this is called three-phase boundary area. And this is where the reaction occurs because the CO2 cannot diffuse deep into the solution to reach the other copper where it's occupied by, covered by the water here. Because we use the alkaline electrolyte, so the CO2, if it needs to penetrate through that water layer, it's going to be converted to the carbonate before it can reach the copper surface here. So that's why we have actually a pretty small amount of this three-phase boundary in the copper PTFE sample. That's why we cannot operate at very high current density. So there are a few different ways we can think of. We can improve the current density. So the first one is that you can make more area of the three-phase boundary area. For example, if you change the rounded surface of the PTFE, you will have more three-phase boundary area. That's one way to improve the current density. But the second one, that's what we try to focus on, is if we can extend that three-phase and boundary here. So instead of having a very small area here, we want to extend it throughout the catalyst layer. So how we can do that? The problem here is because the CO2 and the water are going on the same path to the surface of the catalyst, right? If you want to have the extended surface three-phase boundary, you will need to find a different way that the CO2 can go to the surface of the catalyst, and it should be different from the path for the water. So in other words, you need to decouple the pathway for CO2 and the electrolyte to the surface of the catalyst. So one idea we have in mind is to deposit the surface of the catalyst with a material which is both hydrophobic and hydrophilic, so that it can produce some pore, nanoporous hydrophobic pore to transport the CO2 while you have the hydrophilic for the electrolyte to penetrate through. So that's the idea. So we look at the different monomer and ionomer with the different functional group and different hydrocarbon chain. And we found that the Nafion ionomer with the hydrophobic backbone and hydrophilic polar iron here is work pretty well when we coat them on the surface of the catalyst. So what we did is that we use the spray coating method to coat the copper on PTFE with a thin layer of the Nafion ionomer. And here's how it looks under the microscope. We use the scanning electron microscopy to confirm that we have a thin layer of the ionomer on the surface of the copper. We can also confirm it with the transmission electron microscopy here. So once we confirm that, we test the catalyst in the basic condition. And we use both the copper and silver to prove that it is not just depend on direction, but on the catalyst. But the point here is to improve the gas transport throughout the catalyst layer. So as you can see here for the silver catalyst, without the ionomer, you will have the limiting current for CO2 current is around like 50 milliamp. And for the copper, it's on like kind of similar. When we run in, this one is the 7 molar potassium hydroxide concentration. Now, in a contrast here, when you have ionomer coated on the surface of the catalyst, like silver or copper, the current density increase a lot. So the limiting current, we have not reached it yet, but is about an order of magnitude increase compared to the sample without ionomer. So definitely, when you have the ionomer on the surface of the catalyst, it helps to bring more CO2 to the active side so that you can operate the system at much higher current density. So in this case, for the copper, we also run at like 500, more than 500 milliamp. This is the partial current density for CO2 reduction, and it's not the current for hydrogen evolution is not included. So the actual current is much higher. And based on that observation, now we have a thin layer of the catalyst that we can operate at around like 500 to 700 milliamp current density. What we want is that we can improve to improve the current further. So what we did is that we use the same like copper on PTFE sample, but we want to add another layer of the copper nanoparticle with the PTFE with the Nafion on the surface of the 2D sample here. So we call it the 3D, the copper-based sample. And as you can see here, we have the copper nanoparticle on the top of the copper PTFE sample, and it shows from the TEM image that we have, the thin layer of the ionomer like coated on the copper nanoparticle. And with this sample, we can operate the CO2 reduction at much higher current density, achieving around like 1.3 ampere current density. That's a partial current density. And with a pretty good selectivity of around 60–65%. So by optimizing the gas transport through the catalyst layer, we can achieve like very high current density, similar to the current density in the water electrolyzer. So that is about like the controlling the gas transport throughout the gas diffusion layer and the catalyst layer. What else can we do with the copper on PTFE? So over the past few years, we work a lot on trying to optimize the catalyst layer. So starting from the same copper on PTFE, but we can modify the surface of the copper with the different oxide and different metals so that we can make a hybrid sample for like producing the different products like ethanol, for example. The second strategy that we applied is to control the morphology of the copper. So first, we deposit the copper on PTFE, and then we use the surface reconstruction technique to change the morphology to and the oxidation state and the phases exposed of the copper to tune its activity. And the last one is to coat the copper surface with the different polymer, with the different carbon layer, so that we can make the 3D active side kind of like a confined space between the copper and another layer, so that we can change the reaction pathway. So those are like different techniques that we have been using to improve the performance of the metal on PTFE catalyst. So with that, I would like to conclude my talk by talking about some of the outlook on how we are going to design a better CO2 reduction electrode. So the first point is that the PTFE-based gas diffusion electrode is good, is stable, but there's a problem with the scale up, because when we scale up the system, like the conductivity of the carbon and graphite is not enough, and that's very challenging. The second thing is that like managing the carbon dioxide and water and electron is not enough for the CO2 reduction, because in the actual system, you will have the other cation, so that can form the salt in the gas diffusion layer, or like you can produce some hydrophobic products like ethanol and propanol that can penetrate into the gas diffusion layer. So that is also makes up the system that is quite challenging to overcome. And the last one is about like making the gas diffusion layer that can work under the neutral pH condition. So the example that I show here, we operate in the alkaline media to improve the selectivity for ethylene and ethanol. But there's a downside for that approach is a lot of carbonate it consume, CO2 it consume in the electrolyte because it formed the carbonate. So in order to avoid that problem, you would like to operate the system in the pH neutral condition so that you can avoid the formation of the carbonate. And in that case, you can also integrate your electrode into the membrane electrode assembly configuration, which is more easily to scale up. And with that, I would like to thank my previous group because all of this work I presented here has been performed when I was a postdoc in Sargent Group at the University of Toronto. So I would like to thank my previous supervisor and a lot of my colleagues and sponsors. And thank you. I'm happy to answer your question.